We are finally officially in chapter 5, where we learn about integration. Today we're taking a sidestep from anti-differentiation, and we're talking about something that has absolutely nothing to do with it. Area. And that was a sarcastic absolutely nothing if you didn't notice. So, you can see from the title picture of chapter 5. Okay. Delayed reaction to my trying to zoom. Okay. That we can approximate area between the x-axis and the curve of a function using rectangles. And the more rectangles we use, the better the approximation. You might be asking, why rectangles? Because they are definitely not ideal to use in an approximating area under a curve. Yeah. Yes. Oh, that's okay. Because if I weren't, you just saved the day. Now, in section 5.1, I'm going to talk about the distance part tomorrow. Also, for your homework, I have a worksheet for you. You will appreciate that I'm not giving you homework from the textbook for this. I'll explain why once we see some examples. But I just to admit it's an older worksheet. I've got the title on the side so that I could. This is back in the day when I taped stuff. But it's a short worksheet. It's to the point, exactly what I know you need to take a look at, so it still works. All right. So the area problem. Okay. Do I have to click on you to make you scroll? No, that was delayed reaction again. Okay. So if I'm wanting to approximate the area between a curvy function and the x-axis between particular x coordinates A and B, how am I supposed to do that? You know, we can find areas of shapes that have straight sides. We can do circles, but how do we do this? So we start off with the idea of approximation. Now, on the AP exam, there are certain approximation techniques that they expect you to use. And so today is just all about those approximation techniques, not about actually coming to finding the actual area yet. We're going to be doing that throughout the week. So Riemann sums. What I tell people is when you see the phrase Riemann sum, just think rectangular sum. Riemann rectangles. Because that's what it stands for. It's about rectangles that touch the curve with a part of the top of the rectangle. So a left Riemann sum. And let me get my highlighter out. The left Riemann sum is where we have cut the x-axis up into sections. And for each section, the left x coordinate is plugged into the function, and that is decided to be the height of the rectangle for that entire x interval. So it's using the leftmost x coordinate of each of these little sub-intervals, and we call it a left Riemann sum. So, any guesses on what a right Riemann sum is? Oh. Yep. There you go. Picture of a right Riemann sum. Now, some things to make sure to be clear on. Different words get used for cutting the x-axis up into a bunch of pieces. And I pre-highlighted a key thing to be aware of. When they talk about the number of subdivisions or partitions or subintervals, they're referring to the x-axis being divided up, a segment on the x-axis. Now there's uniform and non-uniform subdivisions. So cutting the x-axis up into pieces can be done uniformly, where each of these distances is equal, or non-uniformly, where each of these x intervals is not equal. Whether it's uniform or non-uniform, we can talk about a left Riemann sum versus a right Riemann sum. And this is demonstrating a left Riemann sum of 3 rectangles with non-uniform and uniform widths. Now, I will sometimes call them widths because they are the widths of the rectangle. And another very important thing to realize is they are little tiny changes in x. So we will often use that symbol delta x to represent the widths of those rectangles. And delta is usually present when we're talking about a change in a quantity. So delta x. In fact, delta y over delta x is another way to write dy dx. And it's a bit of where, it's actually where that d comes from and why we can't use d for distance anymore. It comes from delta. Darn delta. Took the d away from being able to use it for distance. Okay. So I've got a fun, does anyone want to have fun playing along on Khan Academy? Because it can be really fun if you get to be a little bit more interactive. And I actually ended up taking snips from Khan Academy. So what I'm going to do is I'm going to grab, where did you go? This. So I took little snips from this because it had just much better pictures to work with than the textbook did. And I found that I can actually click Google Classroom, and then I can say, choose a class, period 2, choose action, create material, and then go. And then I'm just going to put not an assign, or for fun. In other words, you don't have to. And I posted it, and then you got the link right there in Google Classroom. Super exciting that I can do that. And this just gives you the opportunity to be able to click some things like this one. It may be super simple, but it's at least better than just sitting here listening. What kind of Riemann sum is described by the diagram? Choose one, left or right. So you can have fun with that. I hope you at least appreciate that I'm trying to create some interaction because I know how much that helps. I'm a little bit down the line from where I was showing you. And this is an example you can look at yourself. Okay, come on. There we go. So we are approximating the area between y equals h of x and the x-axis from x equals -2 to x equals 4 using a right Riemann sum with 3 equal subdivisions. I'm going to start with 3 equal subdivisions. So all you have to do is cut that interval into 3 equal pieces. And notice that each of these 3 equal subdivisions has a length of 2. And I'm just emphasizing that these are little delta x's. And then we want to use the right Riemann sum. So that means that for subinterval number 1, I am going to use x equals 0, the rightmost x coordinate of that subinterval. I'm going to plug it into the function. And then I'm going to call that a rectangle from x equals -2 to 0. And if you look at that, you might be wondering, why would you approximate area like that? Look at it. No one would approximate area. Not this figure, not there. But it's not too bad if you go to the next couple of subintervals. So subinterval number 2, the rightmost x coordinate is 2. Plug it into the function and call that the height of the rectangle from 0 to 2. And then again from 2 to 4, take the rightmost x coordinate and call that the area. So while you would never use this for your area approximating, let me explain to you why I'm not giving you the textbook's problems. The textbook problems will give you something like this and ask you to cut this up into 6 equal subdivisions or 8 equal subdivisions. And if you can imagine how tiresome that is, that's why these are horrible approximations. These are horrible approximations so that you don't have to be tortured. You would let a computer program do a good approximation. If you have to sit here and by hand crank out the numbers, it's not worth your time. All you're doing is you are showing the AP test that you understand this process and what it is. So what I would recommend you write if this was a free response problem is you are taking that delta x. Got to wake my pen back up. There we go. You are taking that delta x and you are multiplying it to h of 0. And again, the function is h of x. Plus that same width times h of 2 plus that same width times h of 4. Now, if those widths are different, then you can write those down. If they are the same, you can feel free to, instead of writing it this way, you can factor that equal width out and then just add these values together. Either way, perfectly fine. But it's valuable for you on free response to emphasize the formula. Whoop. Oh, I thought I changed it to highlighter. There we go. It's important to emphasize the formula in free response. Now, after you've got the formula written out, you throw the numbers together. And if you are in free response, do not add those numbers together. If you add wrong, you just lost all of that. And it's horrible. It pains me when I'm grading practice AP exams and I see that. It's right there. And then you decided to make a next step. So just write the numbers. The equal width is 2. And then h of 0 is 4. H of 2 is 6. And then lastly, h of 4 is, again, y value 4. Literally just leave it. I don't care how tempted you feel like you should add those numbers together. It's easy. Yes, it is. Move to your next problem. But if it's multiple choice, like this one actually is, if you're looking at it on Khan Academy, you've got multiple choice to pick from, and you can have fun with that. I've got another example for you. A lot of times they will ask you to approximate area, and they're going to give you a table. So this is specifically saying we're going to approximate the area between the x-axis and the graph of f from x equals 1 to x equals 10 using a right Riemann sum with 3 equal subdivisions. Now, if you look at it, as you go from 1 to 4, that is one subdivision. 4 to 7 is a second. 7 to 10 is a third. Whenever they give a table of values, it's very clear what the subdivisions are. Sometimes they will just, if it's unequal subdivisions, they will say something like, according to the table, create a certain number of subdivisions, and there is no option. If these numbers, 1, 4, 7, and 10, were not equidistant, and they asked you to create 3 subdivisions, would you realize out of those 4 numbers, 3 subdivisions is purely just from one to the next? There's no other option there. So there's enough information to figure out what they're referring to. Now, here's another huge recommendation. Do you know how easy it is when you've got to look at a table, write a number down? Look at a table, write a number down. Do you know how easy it is to write the wrong number? Way too easy. So I recommend that you circle the numbers you intend to write down first, then write them down. So it says a right Riemann sum. Now, for your first x interval from 1 to 4, 4 is the right x coordinate, 8 is the function value that is the height of your first rectangle. Your second subdivision from 4 to 7, 7 is the right x coordinate, 3 is the function value, the height of that rectangle. And then from 7 to 10, 10 is the rightmost x of that interval, and its function value is 5. So you intend to write those 3 numbers down. And then also take the time to carefully check this is a distance of 3. I'm laughing because I can't tell you how many times I myself have done these AP problems and just looked at 4 minus 1 and went 4 or something like that. And it's silly, the things that you shouldn't mess up on. But anyway, so what you're going to do is you are going to write down either individually 3 times plus 3 times plus 3 times, or you can factor the 3 out and just write those numbers. I would recommend on the AP exam that you specify before you write these numbers out that these are f of 4, f of 7, f of 10, so that you are showing them I understand where these numbers are coming from. This is the formula I understand, that kind of thing. All right, so that's that example. Some examples I'm going to skip over due to time, and then I will come back and do them as you leave off for lunch, and you can go back and see the examples. Let's do this one. You might just be given a function. And so with this function, h of x, you are told that you're going to approximate the area from x equals 0 to 1.5, a right Riemann sum, 3 equal subdivisions. So you're going to draw this thing out. From x equals 0 to 1.5, I'm cutting the x-axis up into 3 equal subdivisions. So make sure you do that correctly, and I'll draw a little bit of this graph. Just a mild attempt at it, not the perfect graph. I'm hoping you remember what the graph of 1 over x looks like. The most beautiful symmetric function. Oh, it's just amazing. So much symmetry. So much asymptoting. And it's one of those functions who can say, I am my own inverse. Thank you very much. Anyway. Now, knowing that this asymptotes at 0, you can be grateful that it said right Riemann sum. Now, is anyone curious, though? If I start talking about what if there was a left Riemann sum, how would you approximate this kind of area? Anyone curious? Is there an area to be estimated? Is it infinite? Is it finite? How do you know? Because I will tell you this. What about the graph of 1 over x squared? Okay, now I just couldn't resist. 1 over x squared. Actually, no, wait. Wrong direction. Sorry, 1 second. 1 over the square root of x. It also asymptotes, but it's only quadrant 1. And I'm not drawing it right. What do you think about this function's area as it asymptotes? Do you think that one is also infinite? And I'm going to tell you, I'm not going to prove it to you right now, because I'm going to make you desire to go on to second semester calculus. If you want to know why one of these is finite and one of them is infinite, you need to go on to second semester calculus, and we get to take a look at that in the BC class. It's fascinating. It blows me away that I can look at these two graphs that both have vertical asymptotes, and one of them is contained and one of them is not. And only through the math do you know. Your eye is never going to tell you those secrets. Only the math reveals it. Anyway, I went off on a tangent there. Okay, 3 equal subdivisions. Have you found those numbers? So you've got a 0.5 and a 1. And it's a right Riemann sum. And you don't have to draw the graph accurately. In fact, you don't even have to draw the graph. You just have to understand what you are plugging in and where. So each of these delta x's are a length of 1/2. I don't want to write 1/2 3 times, so I'm going to factor it out of the 3 areas of the rectangles, and then I'm just adding the heights together. And I am plugging these 3 numbers into this function. And so 3 divided by 1/2 will give me 6. Plugging in 1 is 3. And then 3 halves. 3 divided by 3 halves is 2. And if it's free response, leave it there. Don't let the temptation to add get to you. Not in the middle of the AP exam anyway. All right. You will often be asked whether your left or right Riemann sum is an overestimation or an underestimation. So, this one right here, and I think this is one of the problems you can click on if you like. Is this Riemann sum an overestimation or an underestimation? And do you see that what they're referring to is this is a right Riemann sum, and the purple is the area of the rectangles and that blue curve. What's extra purple under the curve is the actual area. You can see it's an overestimation. Your question is, what determines the over versus the underestimation? What about the function determines it? And anytime that I need to figure out whether I need a, what was I trying to say? I'll come back to this example. Anytime I need to determine what about the graph gives me an overestimate versus an underestimate, I like to draw a degree 3 polynomial like this, because if I can't remember whether it's the first derivative or the second derivative and positive and negative, this has it all. This has positive derivatives, negative derivatives. This has positive second derivative, negative second derivative, and you can see them all at once and figure out exactly what matters. So let's say we're looking at right Riemann sums. So if I'm doing a right Riemann sum, then I'm taking a right x coordinate and making a rectangle. Now, I don't really want to sit here drawing this many rectangles. You just need enough to figure out for yourself what matters. I can see that this is an over and over. This middle one is questionable. This one is definitely under. That one looks, Well, it's a little bit questionable. I'll just go there. This one, do you see that this is definitely over? So taking out the ones that are possibly questionable, what is it that you see determines whether that right Riemann sum is an over versus an under approximation of the area under F? So what is it about F that determines whether this right Riemann sum is an over versus an underestimate? I should have drawn a better picture. Let me, hold on. This needed to be drawn better. Maybe this helps a little bit. The thing is, when you're kind of like right in between a change, this one is under great question as to whether it's over versus under. We're looking for a clear cut for sure. Because if they're going to ask you this question, they're going to base it on, in this situation, whether F has a positive or a negative slope. Did I just not draw very good pictures? Perhaps I should depend on Khan Academy's pictures. So this is what they showed, but they just showed one particular section. If you do a left Riemann sum, can you see that you are definitely having rectangles that go above the curve? And if you are doing right Riemann sums, that you are definitely looking at area that is only under the curve. So they've got this fun little interactive thing right here where you can sit there and click, is the left Riemann sum entirely above or below the curve? And we discovered that one was above. And then is that an over or an underestimate? An overestimate. And then if a right Riemann sum were drawn, it lies below the curve, giving you an underestimation. Now, the thing is, at the end of today, you're going to see why I say that you don't want to just necessarily flat out memorize that you're looking for slope or you're looking for concavity, because those can get mixed up as you memorize things. You want to know that if you're asked about an over or an under approximation, you're either looking at slope or concavity, and you need to draw some pictures to remind yourself of what it is that matters. And if I drew an entire concave down graph, and I drew little right Riemann sums or left Riemann sums, if any of those rectangles lie entirely above or entirely below the curve, then that is showing you what matters. When I have a positive slope, my right Riemann sum is above. When I have a negative slope, my right Riemann sum is below. But if I start drawing stuff in the section where it changes from a positive to a negative slope, I can get a drawing that's questionable. They only ask you this when these are sure answers, absolutely beyond a shadow of a doubt, sure answers. So these problems that they give you are set up with certain information that they expect you to find that will say the answer for sure of whether it's an over and under approximation. So what you want to just remember is when it comes to a left or a right Riemann sum, the question of is the first derivative of the function that you are graphing, its first derivative, is it positive or negative? And I'll warn you that sometimes you'll be looking at a graph of, say, G prime. If you're looking at G prime and you want to know if the right Riemann sum is an over and under approximation, you actually have to look at, quote, G double prime being positive or negative. So just whoever the graph is, you're focused on, is it having a positive or a negative slope? In other words, is it increasing or decreasing? And I believe I have an example set up for you. Yes. Okay, so this is an example of what you might see on an AP exam, on a free response AP exam. The table gives select values of the continuous and increasing function g. We've got x, we've got g. First, find the left Riemann sum. So everybody's working. Left Riemann sum of g over this interval for equal subdivisions. Can you hear my extra noise? Okay, let me know if you can hear extra noise, because then I want to make sure that you're not hearing it. So 4 equal subdivisions from -2 to 3, from -3 to 8, from 8 to 13, from 13 to 18. 4 subdivisions. And 3 minus -2 gives me a delta x of 5, and all of them are a horizontal distance of 5 units apart. If I want the left Riemann sum, then I'm going to take the left y values. So left x coordinates y value, left x coordinates y value, left x coordinates y value, and left x coordinates y value. Circle them. Then write it down. I will say, if this is free response, it is best if before you write this down, or, write it elsewhere, that you understand that 13 is coming from plugging into G the x coordinate -2. This, again, clarifies to the grader that you understand what you're doing, and didn't just randomly choose some numbers and cross your fingers. Yeah. So when you write it this way, it's saying which x coordinates are going into the function, and that is part of the entire process, is knowing which x's on each subinterval are plugged into the function to find the vertical distance. And then you do have to put in the actual numbers, but you do not have to add them together. Next question. Is this approximation an overestimate or an underestimate? Now, if you are just thinking, okay, What do I need to look at? What matters with left and right Riemann sums being an over or an underestimate? Perhaps you remember that it's about the slope of this graph, G. Or maybe you don't remember and you have to draw some pictures to figure it out. From here, I call it an Easter egg hunt. Do you see anywhere where it gives you some information to answer that question? And honestly, I feel like free response problems on the AP test are often Easter egg hunts. You need to know what you're looking for, and it's a lot easier to find it if you know what you're looking for. But they did not throw it out there, obviously. So you want to remember that what matters is whether G prime is positive or negative. But you want to also think about what are other ways to say the same exact thing. The same exact thing could be G increasing, G decreasing. And if you think about the different ways this could be expressed, you can then go looking for it. And do you see it? I'm going to highlight it. Easter egg hunt. Now, I want to also point out to you that they said this was a continuous function. Anytime they give you a table, if they do not tell you that this function is continuous, assume that it is not continuous. Unless they tell you that this is differentiable, assume that it is not differentiable. So the key thing was it said that G was increasing. And so if you draw a picture of an increasing function, maybe you draw it this way, maybe you draw it this way, but an increasing function and a left Riemann sum. You should see that despite the concavity, if that function is increasing, this is creating an underestimate. Now, you need to make sure that you state that this is an underestimate because of two things. Because it is a left Riemann sum, not a right. Yeah, well, can you imagine what the AP graders read handwriting-wise? That's why I've never wanted to become a grader, because I do not want to decipher handwriting when I'm not having to work, if that makes sense. Anyway, so then you need to say that the problem point out that G was increasing. So and, that's my and symbol, G is increasing. So just know that when you are explaining yourself, you're giving one of these types of explanations. And very important, don't say, and it is increasing. Don't say, and the function is increasing. You have to state who, because in an AP problem, they are never talking about one individual function. And if you do not overtly say this function doing that. They don't know that you know which function matters, and thus you do not receive credit. So don't pronoun. All right, continuing on. So that was left and right Riemann sums. I have separately a midpoint Riemann sum, because the midpoint Riemann sum, you will never, ever, ever be asked, is it an over or an under approximation? And if you take a good look at this picture, you can see why. You will never be asked that question for a midpoint Riemann sum. And all you need to understand about a midpoint Riemann sum is they're still going to tell you subintervals. So you've got your subintervals. But when they say midpoint Riemann sum, you are expected to know that they mean the midpoint of each x subinterval. So the midpoint along the x-axis, those are the x's that are plugged into the function and determine the height of the rectangle for that subinterval. And I've got a quick example set aside for midpoint Riemann sum, because from what I've seen, they'll typically give you a table, and it'll be a table that's got a good amount of data, because it takes a good amount of data to get the midpoints. So let's read this problem. We're to approximate the area between the x-axis, and you've got to be careful because they will sometimes, you don't need to worry about the fact that this is f prime because they're giving you values of f prime. So you are still looking at area under a curve. It just happens to be named f prime. We are using a midpoint approximation. Sometimes I'll see them say a midpoint Riemann sum with 3 subintervals of equal width. So let's take a look. And if I'm cutting up 0 to 6 into 3 equal subintervals, then I am going 0 to 2, 2 to 4, and 4 to 6. For the first x interval, the midpoint on the x-axis is 1, but 3.5 is the height that I need to write down. In subinterval number 2, the midpoint of that x interval is 3, and the y value of that 3 is 0.8. And then third subinterval, midpoint along the x-axis is 5. You're going to plug 5 into the function. So if you are approximating the area underneath the graph of f prime, then this is a width of 2 multiplied by f prime of, almost messed that up, f prime of 1 plus f prime of 3 plus f prime of 5, which is then these guys. What time are we at? I don't know why, but my mind is forgetting whether I said something to you or not, and it could just be me getting older and forgetting. I talked to you about, I I did talk to you about the difference between uniform and non-uniform, right? Wow. Frustrating getting older and trying to remember, wait, I said that to period 1. Did I say it to period 2? Oh, here we are. Okay. Now, the other type of area approximation that the AP test goes through is trapezoidal area. And if you look at this drawing, you can see that it is a far better way to approximate area than a rectangle. Now, make sure you understand that when they say trapezoidal area, what they are doing is they are taking points on the actual graph and they are drawing straight lines between the points. Straight lines. Those straight lines create the non-parallel side of the trapezoid, or it creates one of the pair of non-parallel sides. So that makes, stop. And by doing that, that makes this perpendicular length between vertical line segments be the height of the trapezoids. So we think of them as the heights of the trapezoids because we usually see trapezoids that are the opposite direction than this. And but that is the delta x. Now, I'm a little low on time, so I'm going to have to just kind of power through this. The area formula of a trapezoid if you don't remember, one way to look at it is to make a diagonal and see that you have the area of two triangles. Triangle with base 1, triangle with base 2, and they both have the same height. And the area formula of a triangle is base 1, or the base times the height divided by 2, plus the area of the other triangle, its base times the height divided by 2. Or you can look at it as this is the average of the bases being multiplied by the height. So if you are able to find the average of these two lengths, then you can actually make a rectangle out of that with an equal area. Just find a way for you to remember this formula. Then, for this particular example, we are looking at the trapezoid number 1 has an area of the base 1 is plugging 2 into this function. So 3 times the natural log of 2 plus the length of base 2 is plugging 4 into that function, 3 natural log 4, and then divided by 2 times the delta x, which in this case is 2. And then I have to sit here and literally do this for each individual trapezoid and then add those areas together. So my next trapezoid is going to be found, one of the base plugs 4 in again. The other base plugs 6 into the function. And I divide that sum by 2 and multiply by the delta x, the height of the trapezoid. And then for the next one, 6 is plugged in, 8 is plugged in, and then continue the formula. Add those together, you have your area approximation. You very well might be asked if a trapezoidal approximation is an over or an underestimate. And this time it's about concavity. And I was going to give you a little bit more time to think about it, but we are down on time. So if you look at a concave down graph and you draw a straight line between 2 points, you are looking at an underestimate. But if you are looking at a concave up section of the graph, you can see that it is actually going to give you, this is kind of in between, so that one's an unfortunate one to draw. And I'm going to talk through these examples at the end of the video after you guys leave class. So know that what matters is whether the function has a positive or a negative second derivative. You don't need to memorize which one gives you over, which one gives you under. You just need to be ready to draw it. If you draw it, you can see the difference between an overestimate versus an underestimate. I've got one more thing to throw your way, and I intended to have more time. This is not approximating area, but there are only certain times that you are asked for overestimate versus underestimate of something. Either you have a left or right Riemann sum, and it's an over or an underestimate of area, or it is a trapezoidal approximation of area, and then it's based on the second derivative of the function, not the first, and you're approximating area, or you are using a tangent line. And let's say I'm looking at, the tangent line is at A, and let's say I want to approximate f of B. Actual f of B is here. My approximation from the tangent line is down here. Can you see that that is an under approximation? It too is based on concavity. In fact, you remember the definition of concavity is actually about whether the tangent line is, oh, you can leave for lunch unless you want to keep hearing. It is about whether the tangent line is under or over. A concave up graph has a tangent line under the curve. That will create an underestimate of the y value of the function. If you are dealing with concave down, your tangent line lies above the curve, and then any estimate of the function will be an overestimate. And phrases that are important that you need to be ready for, they will say linear approximation, they will say linearization, local linearity. They all mean tangent line approximation, and they have to give you a very specific x coordinate of a very specific function. Once you know the x coordinate and which function you're using, you can create these formulas that I covered up by using the point slope form of a line. And point slope form of a line looks at y minus the y coordinate of this point. And if my function is f, then the y coordinate is f of a, is equal to the slope at a multiplied by the change in x, x minus a. And then all you have to do from there is add f of a over to the other side to get the formula for a linear approximation, which we have looked at before, but I wanted to say it again here because of the issue of what do we look at to determine if it's an over or an under approximation. Okay, so you guys go to lunch, and I'm going to keep recording, and I'll go through some examples to make sure people have it. And I will start with this example. A differentiable function has the property that we know what f of 5 is. We know the slope at 5. You are expected to come up with an estimate for x equals 4.8 using the local linear approximation for f at x equals 5. So you want to get used to these phrases and understand that all it's saying is equation of tangent line. And when it comes to equation of tangent line, you can go straight for y minus the y coordinate equals slope times x minus the x coordinate. And then if we are estimating the function at 4.8, all I really have to do is plug 4.8 into this x and isolate the y. And boom, you've got it. And you would have a calculator on this one. You can see when it goes decimal, that's when they allow a calculator. And 4.8 minus 5 would give you negative 0.2. From there, let a calculator find it. Then I've got a second example where it asks for not just the approximation, but is it an over or an underestimate? And this is presented a little bit differently. It's giving you a differential equation, and it's telling you that you are looking at function f, and the graph of f passes through the point 1, 2. That is dealing with, that is the point of tangency. And it tells us that we are dealing with concave down when we are in the interval from x equals 1 to 5. Now, k is an approximation for f of 1.2. So if I'm looking at an x-axis and at the point 1, 2, I've got my point of tangency and I'm concave down after I hit 1. So I'm concave down. Maybe I'm increasing, maybe I'm decreasing, but I know I'm concave down. Then if you draw a tangent line with that concave down, either it's this or maybe it's this, either or, you should see that it's an overestimate with that particular concavity. And so that gets you to, it's an overestimate. And then the question is, which of these two is it? And then you want to be careful. Equation of your tangent line, y minus the y coordinate of f. And sometimes you have to do another Easter egg hunt and try to find what is this y coordinate. They had to tell me somewhere. Let's see, f is a function, graph passes through, oh, there we go. There is the y coordinate. So y minus 2 is equal to the slope, which I'm leaving a parentheses to come back to x minus 1 for that point of tangency. To get the slope, I've got to plug in this xy coordinate into this differential equation to find the slope. So I plug in 2 into the y, plug the 1 into the x, and I get 3. And now I know that my y is approximately, add the 2 over, 2 plus 3 times, oh, I didn't put the x, oh, x minus 1, where we are approximating 1.2. So I'll plug into that x 1.2. 1.2 minus 1. And then I can see that it's 2 plus 0.6 and get the correct answer. So that was the tangent line approximation example. And now I'm going to go back to some examples I skipped. And let's see, what did I first skip? We did that one. What did I first skip? I started skipping with the trapezoidal approximation because I was running out of time. So we did this first one where we estimated the area using the trapezoid. And then I started drawing in this diagram. But this diagram, let's see what it is saying. It is saying approximate the area between g of x and the x-axis from x equals 2 to x equals 6 using a trapezoidal sum with 4 equal subdivisions. So if I'm going from 2 to 6 with 4 equal subdivisions, then these are the cuts along the x-axis. Each of those is giving me a delta x of 1. In the trapezoidal approximation of area, that's the, quote, height of the trapezoid. And let's remind ourselves the area formula of a trapezoid is base 1 plus base 2 divided by 2 times the height. But when it comes to our trapezoidal approximations in calculus, the bases are function values. So I'm looking at base 1 is a value of my g function with a particular x plugged in. Base 2 is a value of my g function again with a different x plugged in over 2, and then the h is delta x. So for each of these trapezoids, my delta x is going to be 1. That's going to save me a little bit of time. Now what I'm going to do is I'm going to draw the bases for trapezoid number 1. Those are my 2 bases. A straight line creates that quadrilateral that is a trapezoid. The base values are 3 and 7. So the area of trapezoid number 1 is 3 plus 7 divided by 2 times the delta x of 1. Then I move on to my next trapezoidal area and add that. And I have that one of the bases is what we just used. And then the next base is found by plugging 4 into this function. And so I am now looking at my bases of this trapezoid are 7 and 6. Add them, divide by 2, multiply by the height. And I'll go a little bit faster now. So I've got trapezoid number 3. One of the bases is length 6. The other base is length 4. I add 6 plus 4, divide by 2, and multiply by the height. And I'm going to draw a straight line to emphasize it. And then lastly, finally, we have base 1 is 4 used again. Base 2 is found by plugging 6 into the function, which happens to also be there at 4. So I am getting base 1 plus base 2 divided by 2 times the height. And you can see that if it does happen to be a rectangle, the trapezoidal formula will still work exactly the right way, because what is base 1 plus base 2 divided by 2? It is the height of that rectangle. And so that problem, the area approximation is whatever number those add up to be. Now, for this one, it's a challenge problem. Choose the expression that uses 3 trapezoids to approximate the area under the function f on the interval from -1 to 5. So to emphasize, -1 to 5. And you can see trapezoid 1, its height, trapezoid 2, trapezoid 3, those heights. Now this time you don't see the y values, so you're just going to say the y values are, for here, f of -1. For this length of the base, f of 1. So I have base 1 plus base 2 divided by 2 times the height, which is the delta x, and this delta x is a length of 2, and that's trapezoid 1. Then trapezoid 2 is going to be found when I take the base value when 1 is plugged into the function, as it had been over here, when 3 is plugged into the function. Those are my two bases, divide by 2, multiply by the, quote, height of the rectangle, which is delta x. And then quickly I'll write that my third one is plugging in 3 and 5 into the function for the two bases. Add the bases, divide by 2, multiply by the delta x, or height of the trapezoid. And let's see what the multiple choice answers are and figure out which of those it is. Now, if I look at what's going on here, these 2's are canceling. And I'm ending up getting f of -1 plus f of 1 for trapezoid 1. F of 1 plus f of 3 for trapezoid number 2. F of 3 plus f of 5 for trapezoid number 3. These two are at this. When x is 1 is added twice. When x is 3, this is added twice. Now let's take a good look at which one of these represents that. And perhaps you see it. And D would be the correct answer for that trapezoid rule. And it's actually uncovering a trapezoid rule formula. It's a great formula, but I take caution in throwing it out there for prepping for the AP test, because you usually have to show your trapezoids one at a time anyway, and it's better if and they will often give you unequal delta x's. So it's better to just know the area of a trapezoid formula and how to use it, because then you can get the correct answer, whether you're dealing with uniform subintervals or non-uniform subintervals. And I think that actually takes us through all the examples. So I hope you enjoyed this approximation day, and I will see you tomorrow for more good fun.